Okay, good morning to all of you. So is my AV is okay? Thank you. So yesterday we were discussing about the problem which we have, hope I think we have completed I think that one with this plot. So now today let us take this example under optimal system operation, another topic that is unit commitment problem. So actually, this unit commitment problem should come before the economic operation or economic dispatch. Why means you are seeing that one in the economic dispatch, you got two cost equations. That is, two units or two plants characteristics, cost characteristic equation you got, isn't it? C1, C2. So that means what? Again, in these two, which one is better to operate for varying load? That is what we have done it in economic operation. From where did you get these two cost equation? There may be so many units or plants available in a thermal in a one station, isn't it? Suppose if you take Raichur thermal station, so we are having 7 units. So almost of 210 megawatt and one unit of 250 megawatt, isn't it? So 8 units are there total. So out of these 8 units, which unit to be operated for a particular load? So depending on the cost characteristics, the cost will vary for each unit. Like in the 8 units are there in Raichur thermal station, so each unit cost characteristics will be different. Because if you take the first two units that were installed in Raichur thermal station, the cost characteristics, that is cost is less, that is rupees per hour is less, because at that time the power purchase agreement, so that is different, the cost was less, so therefore it will be different. Later the additional stages which came up, the power purchase agreement conditions are different, so also cost has been increased drastically, that is investment cost, maintenance cost, operating cost, etc. So depending on this one, this cost characteristics of third, fourth, fifth, seventh, etc. plants are different, even though they are of same rating of 210 megawatts, first 7 units. Understood? So because of these cost characteristics are different for different units or plants, now we have to find out which units to be operated to meet a particular load, which units to be operated to meet a particular load. Out of 7 units you take, out of 8 units in a Raichur thermal station, you assume it 7 units with 210 megawatts. Not assume, let us take the units with the same rating, that is 210 megawatts. 7 units are there. Out of these 7 units, which units you have to operate it? So this you have to do it for hourly basis. For every hour, you have to analyze. Okay, first hour now, morning 8 to 9, these units we have to switch on. Next 9 to 10, these units to be switched on. These units to be switched off. Even if it is switched on, what is the load? That has to be taken. What is the generation? Suppose if out of 7 units, unit 4 and unit 7 should be switched on. Unit 4 and unit 7 should be switched on between 8 to 9 a.m. Okay, fine. Or three combination of three, you can do it. Say unit 2, 4, 7, you can do it. Or you can take all the 7 units, you can switch on. But this depends on a particular, on hourly basis, you have to analyze this one. You have to analyze on hourly basis which units to be switched on. Understood? So this is known as your unit commitment problem. What is the commitment that you are giving it to a particular unit or a plant? So that is known as your unit commitment problem. Which generators to be kept in on position depending on the varying load, and this has to be done on hourly basis. Understood? So this is known as your unit commitment problem. So out of 7 units, so we may think that, okay, operating 2 units, operating a combination of any 2 units, operating a combination of any 2 units will provide better result. That means cost will be less, cost of generating cost will be less. Then which are those 2 units? Out of 7 units, which 2 units we have to use it? Isn't it? So that you have to evaluate it by solving the coordination equations. Say particular load has been given. For one load, use the coordination equation which I have explained it in economic operation. You know what is coordination equation? Solve it for a particular load during that given time. Again, load will vary continuously. Load will not remain constant. Again, next, whenever the load varies, again solve the coordination equation for all the 7 units. Again, for next change in load, again solve the coordination equation for all the 7 units. So this process you have to repeat till you get a optimal cost. Which 2 units you have to operate? I am saying it 2 units, 2 units. You can operate any 3 units. Only thing is you have to get optimal cost. Cost of generation must be minimized. That is your aim. You operate, suppose 210 megawatt is there, 7 units are there in thermal Raichur thermal station. Suppose if your load is 300 megawatt. So these 7 units, one unit 210 megawatt, another unit 210 megawatt. So totally 2 units 420 megawatt. But what is the load demand? 300 megawatt. But can you operate? If you operate unit 1 and 2, will it be economical to meet the load demand of 300 megawatt? If you operate unit 2 and 4 to meet the load demand of 300 megawatt, will it be economical? So you have to try all these combinations. You have to try all the combinations by solving coordination equations. So obviously you see how many probabilities for each load you have to calculate it. How many times you have to solve the coordination equations. So this computational time or computational calculations will become more and more, and it will become a tedious task. So what is the solution for this problem then? What is the solution for this problem? So it comes your optimization problem. So optimization algorithms are used to solve such type of problems. One such problem is your dynamic programming. One such algorithm which we are using to solve this unit commitment problem is dynamic programming. This is what we are going to study in this session. Okay, fine. Okay, this is the unit commitment is an optimization problem used to determine what you are going to. Just now I have given brief introduction about what is unit commitment, how it is to be solved. Now you got some idea, isn't it? You got some idea what is unit commitment problem. So, and how it is solved using optimization problem. Why you should go for some optimization algorithm? Because you have seen you have to try all the combinations for each particular load. You have to try all the combinations by solving the coordination equation. Each time you have to solve. Again, next hour the load will vary. Again, you try for all the combination, whether you should switch on only 1 and 2 or 1 and 4, 3 and 4, 4 and 7, or you should switch on the combination of 3 units at a time like 147 or 321, or a combination of 4 units, you can say 3 2 3 5 7. So all these probabilities you have to try it by solving coordination equation. But this is, you know, that computational calculations will increase, so therefore becomes a tedious task. So therefore we have to use some optimization algorithm to solve such problems. That is known as your dynamic programming we will be using to solve this unit commitment problem. Fine. Okay, now you see unit commitment is an optimization problem used to determine what we are going to determine. Let me take the pointer here. Okay, what we are going to determine here, operation schedule of generating units at every hour. That's what I have explained it. Each hour, you have to find out operation schedule of the generating units. Suppose 8 to 9. Take Raichur thermal station only. 7 units, total 8 is there. I am taking only the 7 units. Or 8 units you take it. Only the thing is, difference is 8th unit is of 250 megawatt. First 7 units are of 210 megawatt. Total 8 units are there. Now, what is the operation schedule of these 8 units? For each hour, you have to determine morning, say 5 to 6, which are the generators should be on, 6 to 7, which are the generators to be on. Like that, you have to determine. This is the unit commitment problem. But however, with varying loads, this you have to determine the operation schedule of generating units. You have to determine with varying load under different constraints. What are the different constraints? Constraint may be in the form of environment, or constraints may be in the form of your generator limits you have seen. Constraints may be in the form of voltages, etc. So many constraints will be there. So this is your unit commitment problem is used to determine the operation schedule of generating units at each hour with varying load under different constraints. This is the on paper definition. You have to give it. Unit commitment will give you which units to be operated per hour for varying load with different constraints. So this is the thing we are going to study under this unit commit problem. Simple way, it is an optimization problem of determining which units to be on, which units to be on for a given particular load under different conditions or constraints. This is what your unit commitment problem. Why we have to solve this unit commitment problem? Why we have to solve? Obviously, it is not economical to run all units at all times. You take RTPS, Raichur Thermal Power Station, RTPS, I will be using it. So it is not economical to run all the units, 8 units at all times, because the operating cost or the cost characteristics of all these units, 8 units are different. So therefore, it is not economical to run all units at all times. So only thing is you have to find out which units to be kept on during which that means for an hourly basis you have to do it. Now you see for a given load, determine which unit should be kept on is called your unit commitment problem. Already I have explained it, this one. Understood? For a particular load, okay, these are the units to be on. The other units, please don't operate it. So that if you operate for this particular load, so it will be economical because looking into our cost characteristics, so we are going to identify which units to be kept on. You keep in your mind this RTPS only. Keep in your mind your RTPS only, Raichur Thermal Power Station consisting of 8 units. So out of 8 units, which units we have to keep it on for a given particular load. And it is not economical to run all the units at all time. Obviously, I have taken RTPS as an example, thermal station. So why? Because unit commitment is important for thermal plants. It is very important for thermal plants because the load will be varying on this one. Also, operating cost will be considered for thermal plants. In the previous class also, when I started this optimal system operation chapter, I have explained you about these things. So therefore, unit commitment is important for thermal plants. However, it is not important for hydro stations, that is hydroelectric power stations, because what is the fuel used? Water. So where the water is coming, it is free. Apparently, it is free. There is no operating cost almost. So therefore, unit commitment problem is not important in your hydro as well as your nuclear power plant. Why unit commitment is not important in your nuclear power plant? Because nuclear power plants will operate at its base load. Understood? So at its base load. Okay. So your nuclear power plants will operate at its base load. So that means there is no variation in load. Once a nuclear power plant is started with a particular load, it remains the same throughout. So there is no variation in the load. So hardly there is any control existing in the nuclear power plant. Is it clear? That's why UC means unit commitment is not important for thermal station and hydroelectric power stations. However, it is important for your thermal plants because we are getting the operating cost. So this is what I have explained, not important for nuclear and hydro. Nuclear power plants operate at base loads. There is no variation in load. So therefore, there is no control of this load. Clear? So we'll be dealing it with unit commitment problem with thermal plants only. So that's why I've taken Raichur thermal station here as an example. Okay. First, what you will do in unit commitment problem, UCP means unit commitment problem. So first, the most unit must be operated. Most efficient unit must be operated, which is the most out of 8 units you are there in Raichur thermal power station. Which unit is most efficient? Most efficient means what? The efficiency should be high at minimum cost, minimum generating cost. So then only we will call it as it is most efficient unit is operated first. Then as the load varies, the less and less efficient unit must be operated. Understood? First, that is priority wise, you have to prioritize, you have to do it. So first one, most efficient one, you have to do it. Most efficient one, you have to do it. Then as the load varies, which one you have to operate, which unit? The less and less efficient. So unit must be operated. Understood? So this is what I have explained it. Now, all these things I have explained it. Solving coordination equation for each combination of units. I said first unit and second unit you operate. Take these 2 units, solve coordination equation like our economic problem, or consider 3 units 1, 2, 3. Solve the coordination equations to meet a particular load demand, and in turn you find out which is the unit to be operated at which load for economic operation. So this is what I explained it. So computational savings. So considerable computational savings can be achieved by using dynamic programming. This is what I said it earlier. So this dynamic program is optimization technique which is used to solve this unit commitment problem. Understood? So when we have to use this dynamic programming, whenever a multi-stage decision is required, multi-stage. What is multi-stage here? You see that one? Each hour you have to take a decision. This is the one thing. Apart from this one, whether you have to operate 1 and 2 units or 3 and 4 or 134 or 1347, combination of 4 units or 3 units, 2 units or 1 unit alone, this is a multi-stage decision. So whenever multi-stage decision has to be taken, then you can apply DP, dynamic programming is applied when multi-stage decision is required. Now you see the total number of units available. This is the data which is required before starting your unit commitment problem. What is the data which is required before the commencement of your UCP unit commitment problem? Number of units available. Number of units available. Then their individual cost characteristics. So I said RTPS, number of units available 8. What is the individual cost characteristics? That's what I said. First 2 units which were installed long back are having the less cost rupees per hour. That is cost per generation is less as compared to the other units. So it varies depending on that one. Maintenance cost, operating cost, investment cost varies as years move on. So therefore, obviously the cost characteristics of the units also will vary. So therefore, individual cost characteristics is required. And load cycle. Okay, 8 to 9, morning 8 to 9, this is a load. 9 to 10, this is a load. How to get this load cycle? By doing load forecasting. This is another term. By doing a load forecasting means they will take the history, the earlier history, and they will decide, okay, during 8 to 9 this is a load is going to come, from 9 to 10 this is a load which is going to come, 10 to 11 this is a load which is going to come. So this is decided by performing the load forecasting analysis. This is history based one. So load cycle to be known, at stations to be known priori. So all these three things, one is number of units available, their cost characteristics, and the load cycle on the stations. So to be known before solving this unit commitment problem. This is a one thing, first important thing, you should know that one. Without this one, we cannot solve. Now further, the load on each unit of combination of unit changes with a small step size of delta megawatt. That means what you have to do while doing this unit commitment problem using dynamic programming, every time you have to increment the load. Every time you have to increment the load on each unit. This increment should be in a small step size, that is delta megawatt. So therefore, example, it may be in a step size of 1 megawatt. Some stations, some units, they may take 2 megawatts as a step size, or 3 megawatts, 4 megawatts, etc., or zero point 0.5 megawatt. So this step size varies depending on the station. So therefore, the load on each combination of units changes with a small step size. Suppose if you are taking a combination of two units, so step size means 1 megawatt on unit 1, 1 megawatt on unit 2 will be varying. Okay, hope you understood. This is the thing you should know. And step size variation in load, you should consider it as a step size of say 1 megawatt. It depends. But here we will assume 1 megawatt. And we will see how this dynamic program will be applied here. So again, I am repeating it, these two statements which I said it. To solve dynamic programming, these two statements you should assume it and you should start. So number of units, cost characteristics, load cycle on each station to be known or are to be assumed. Then load on each combination of units must be incremented by step size of delta megawatt. Maybe it may be 0.5 megawatt or 1 megawatt. So that's why I repeated these two statements again here in this slide. Okay, now let us see how this dynamic programming will be applied. So in this dynamic programming, we are having recursive relation. So one recursive relation we are having it. Using this recursive relation, we are going to solve this unit commitment problem using dynamic programming. Understood? So how to get this recursive relation? What is this one? Let us see here. Let the cost function fnx is defined as follows. Now remember here, this is your cost function fnx. So means what? This bracketed term x means it is the generation, x generation. That is nothing but in terms of megawatt. In terms of megawatt. This is generation. Understood? This is units. This n indicates it is units. Clear? This indicates it is units. N is units. X is your generation in megawatt. Understood? So that means to generate X megawatt, by n units, what is the cost? That is Fnx. Hope you understood. To generate X megawatt by n units, what is the cost function? Fnx. This is how you should read it. So this is defined as, you see, Fnx is equal to minimum of, you see this one, braces I am having it, and this is the one term I am having it, and this is another term I am having it. Understood. Now what happens here? You see, this is the one term. Understood. This is the another term. We are having it. Fine. So Fn x is equal to minimum of these two terms. Minimum of these two terms we have to consider. Minimum of these two terms. So how to consider these two terms here? Let us see that one. Fn minus 1 x minus y, we are having it. Please remember this recursive. This is known as your recursive relation. Fn x is equal to minimum of these two terms. So therefore fn y, small fn y plus fn minus 1 x minus y. So among these combinations, which is minimum value? So which one you have to minimize? Y variable. That means this y. Understood. So what is the difference between this capital Fnx and capital Fny? Sorry, small fny. The difference is here. Y is again generation. Y is again your generation. What is this Y corresponding to this one? Y corresponding to this delta megawatt. Understood? This Y corresponding to your step size delta megawatt. So what is the step size? We can assume it 1 megawatt, isn't it? So this Y may be 1 megawatt, 2 megawatt, 3 megawatt, 4, etc. Hope you understood this Y. And this is the cost of generating Y megawatt by nth unit, not n units, by nth units. Hope you understood this one. The difference between this and this capital Fnx and small fny. This is the cost of generating x megawatt by n units. N units, I am using plural. What is this small fny? Is the cost of generating y megawatt by nth unit. Nth unit, that means only single unit. Understood? And so therefore, the remaining n minus 1 units, remaining n minus 1 units will take care of the remaining load x minus y. Understood? So I will give it here for clear understanding. You see here, Fn x is the minimum cost. That's why I represented minimum here. Fn x, capital Fn x is the minimum cost in rupees per hour of generating x megawatt by n units. Okay. Now what is small fny? What is small fny? It is not the minimum cost. It is a parameter which is within the minimum function. So it is a cost of generating Fny is the cost of generating Y megawatt by nth unit. That means here it is a single unit, here it is n number of units. That's why whenever n number of units are included, we have to say minimum cost. Okay. Now, what is Fn minus 1 of x minus 1 on the same lines? Can anyone tell? What is this term is known as Fn minus 1 of x minus y? Can anyone tell what is that one? Can anyone tell Fn minus 1 capital N? What is this one? I said this function is cost of generating Y megawatt by nth unit, small f, single unit. Small f means single unit. Capital F means it is plural n units. So this is nothing but cost. But which cost? Minimum cost in rupees per hour of generating X megawatt by n units. Now here also you see this is capital F. So it is similar to this one. How we are going to define Fn minus 1 of x minus y? How we are going to define? Can anyone tell? So yeah, capital F or small f, it is nothing but cost of generation. Understood? So here it is capital F. How we are going to say? Like same thing. Is the minimum cost, okay, some answer I am getting it. Let me check. Minimum cost of remaining units. Okay, very good. That is the location has given that answer. So this one is nothing but capital F, capital F. What is the for capital F? We have written same thing. So same thing you write it for this one. Is the minimum cost in rupees per hour? This one I am telling it. Of generating, instead of X, we are having X minus Y megawatt by N minus 1 units. By N minus 1 units. Cost of production of X minus Y megawatt by N minus 1 unit. Saksham Sharma has given it. Right. That's how you have to write it. Anyway, I have given it. So this is how you should write this one. Okay. Now you see this one. What is Fn minus 1? Is the minimum cost of generating X minus Y megawatt. Minimum cost of generation. Capital F means you use minimum cost. Minimum cost of generating X minus Y megawatt by N minus 1 generating units. You see the same thing. I have written it. That means, so this will take the nth unit. There are n units are there. You assume it there are nth unit will takes a load of Y megawatt. Remaining n minus 1 remaining units will take the remaining load. That is the meaning, isn't it? So hope you understood this one, the recursive relation by using this one. Understood? So this is the recursive relation. So you have to keep it in mind. However, we will be not doing more problems numericals, but for the concept of understanding this dynamic programming, so let us understand. So now you have understood this dynamic programming it. So this is how you have to explain. Now let us take illustration of this TP. How to illustrate this one? Okay. Okay. So illustration of your this one. Consider a sample system consisting of 4 units. Keep it in mind. There are 4 units because if I take a RTPS example, number of combinations will be more because there are totally 8 units and each is of 210 megawatts and the other one is 250 megawatt. So let us take for simple understanding. That's why I'm taking number of units, 4 units. Each unit is rating is 12 megawatts. Rating of each unit is 12 megawatt and the total load is 9 megawatt PD. This is your PD. Understood? 4 units are there. Each unit can take or generate a generation of 12 megawatt and the total load is 9 megawatt. Now out of 4 units, which unit you are going to operate so that the operating cost will be minimum? Which unit? So you may think out of 4 units, you may operate one first unit alone because first unit, each unit is 12 megawatt. So each unit can take a load of 9 megawatt easily because maximum limit on that one is 12 megawatt. So 9 megawatt load it will take. Only one first unit you can switch on. Remaining 3 units don't switch on because it will take this 9 megawatt load. Or some of them will say, so no sir, I don't want to switch on first unit, I will switch on only unit 2. Somebody will say unit 3. Somebody will say unit 4. Or somebody will say, I will switch on the combination of any 2. Sir, I will switch on unit 1 and 2. No sir, I will switch on 1 and 4. So this combination will vary. Somebody will say, I will not agree with the 2 units. Sir, I will switch on 3 units at a time. And somebody will say, no sir, I will switch on all the 4 units. Okay, all are right. But only thing is, who is operating at minimal cost, minimum operating cost, generation cost is the important thing. Understood? So yeah, all the answers are right. But what is our aim under unit commitment problem? minimize, or economic operation is minimize the generating cost or operating cost. So for that one, which combination will be fit? So that's what we are going to see using this dynamic programming. So as I said, what is the, before solving this unit commitment problem by using DP, what are the three things you should know? What are the three things? One is number of units. Yes, it is known. Number of units is known to you. Load cycle. Yes, it is known to us. What is the other thing? Cost characteristics. Cost characteristics. So what are the coefficients we have taken for cost characteristics? Alpha, beta, gamma we have taken earlier, isn't it? So because different textbooks uses different constants. Some textbooks uses like DP Kotari will use AI, BI, DI. AI, BI, DI. Some textbooks, Hadi Sadat will use alpha, beta, gamma as a coefficients in the quadratic equation. Cost function is your quadratic function, isn't it? You know how to represent it. So those characteristics should be known. So the assume it, this is the thing which has been given. The generating unit parameters, there are 4 units, 1, 2, 3, 4. The minimum loading on each unit to be 1 megawatt. You see that one? You cannot shut down completely, isn't it? That is the one more thing which you have to keep it in mind. So this is the 1 megawatt we have to operate it, and maximum is 12 megawatt. Maximum loading on each unit will be 12 and minimum will be 1 megawatt. Now let us see here. What are the cost parameters? Now you see this, I have taken it from DP Kotari book. A coefficients, B and D, they will use A, B, D. A, B, D, they will use it. So here ABD means not AB Devilries. Understood? So these are the constants or coefficients of your quadratic equation. Now they are given A, B and D values are 0 here. For this one or some problem, they will give D also. So then you have to consider the whole thing. Now this is the cost equation. This is the cost equation. So where we have used alpha I here, beta, gamma we have used here, isn't it? So this is what we have used it. But here we are using AI, BI, DI. And with half thing we are using it. Okay. Now what we have to do here, half AI Pj square plus Bi plus P into Pj plus Di. This is your cost of generation at ith generating unit. This is what has been given. This you know it. Now you see, first let us start with only one unit. Let us start with only one unit which is operating at full capacity of 9 megawatt. At full capacity of 9 megawatt. Single combination we will take it. So for that one, the capital F1x is equal to small f1x. What is f1x and this small f1x are same now in this case. Why? What is f1x? Is the cost of generating x megawatt by first unit. That means by first unit. That is nothing but your total cost. That is nothing but your total cost F1x. That means this is nothing but minimum cost of generating X megawatt by 1 units. 1 units. It is not a plural. It is only one is there. So 1 unit. So therefore 1 and 1. So it will be same. When you are considering single unit, then it is capital F1x is equal to small f1x. Clear? Because only one unit you are operating. So therefore, what is the total cost? Is also the cost of that single unit. So that's why capital F1x is equal to small f1x. So now substitute the values. So now I am using it total load of 9. What is this x? Is load. That is 9. I am using it. So 9 megawatt means 9 megawatt load to satisfy how much generation these units has to generate? 9 megawatts only, isn't it? To meet the load demand of 9 megawatt, what is the generation required? 9 megawatts only. So therefore, I'll be using it here 9. This is the generation. Now in the same equation, you write it here, and AI, BI. That means this is what first unit. 1 indicates first unit. So for first unit, what are the coefficients here? For first unit, so the coefficients of A is 0.77. Understood? A, 0.77. What is B? 23.5. I is what here? I is nothing but here, it is 1. I is your 1. Understood? This is 1. So for first unit, what is A and B values are this one. What is D is 0. For all the things, D is 0. That has been given here. Isn't it? So we will not consider this one. So substitute that A and B values from this table. Then what is this PGI? Is nothing but your this one. So this is nothing but your PG. Clear? That is 9. That is nothing but your generation. X is your generation to meet the given load of 9 megawatt. So these values you have to substitute it. So now let us substitute it. Now you see I substituted A 0.77, B 23.5. Okay, next step I will be substituting PG as 9. Is it visible to you? The last line is the last line. This one is visible to you. This one is visible
Yes,
to you.
sir.
Okay, fine. Thank you. Because for me it is not visible. Okay, you can view it because that screen is coming in between. Okay, fine. So substitute this PGI as 9 megawatt here. So half 0.77 into 9 square plus 23.5 into 9. Okay, so that's how you have to substitute it. So the value will be rupees 242.685 per hour or 242.685 rupees per hour. Either way you can find out. Clear? Hope you understood. So here what you are assuming it first, you are operating only one unit. Which unit you are operating? First unit you are operating it. First unit you are operating it. So for that one, what is the cost of generating X megawatt by first unit is nothing but your total cost of generating X megawatt by N units. N is only one unit, isn't it? So that is one. So that you write it. So 9 why we are trying? So only one unit we are operating with a full load of 9 megawatt. So to meet 9 megawatt, it has to generate, what is the X generation? Is it has to generate 9 megawatt of generation. Substitute this value, so you will get 242. That means if you are operating one unit, the cost is 242.685. Okay. Now let us take the recursive relation by dp. Recursive relation will consider the combination of two units. So combination of two units. So you may consider combination of 1 and 2 or 1 and 3 or 1 and 4. Just I will be back 1 minute.